Hello, let's continue on with chapter 16 and the blood vessels. Now, when the common carotid artery, first off, if we're on the right side, it's the the brachiocephalic. The brachiocephalic will then divide into the right subclavian and the right common carotid. Now, I want you to realize that they divide and divide and divide some more. More so that you're aware that there are more detail. Blood vessels go everywhere in the body. You don't have to worry about the specific names of these ones, although some of them are obvious, such as the blood vessels that feed the vertebrae are the vertebral arteries. Good. Now, a very complicated set of blood tissues or blood vessels are feeding the brain. I do not want you to know all these names, but I do want you to be aware of something called anastomosis. And anastomosis is the ability to have the important areas fed with more than one blood vessel. So let me find the word anastomosis because I want you to see the term so you're aware of what the term is. It's not here. We'll come back to it. We'll come back to it when we come to it. Okay, so it's a circle. It's called the circle of Willis. And this means that the blood supply can go in more than one direction in case there's any sort of a blockage and you have a communicating artery. Very efficient in the fact that you can get blood to the area in more ways than one. However, it's very weak at these junctions, and this is usually where you will have, if you have an aneurysm, which is when a blood vessel fails, it happens there. Okay? We'll find the term anastomosis later. Good. Next, I want to look at is where you get your pulse from. Most common place to get your pulse is taken on the radial artery, which is above the radius. Okay, radial artery. Then you have your brachial artery is where you take your blood pressure. Often if you're taking it on your neck, it's a carotid artery. If there's some damage to your arm if there's some damage to your arm, you will take it from your femoral artery. And in small children, this is where you take your dorsal pedis artery, either on the top of the foot or on the back of the foot. Okay, good. That's where you get your pulse from. And a pulse is just a measure of the blood pressure. And we talked about the measure of the pulse is just the contraction of the heart. Okay. Things are slowing down. I don't like this. Now, let's go to the veins. The veins can be confusing in the fact that they seem like they have the same name as the arteries, and some of them do, and some of them don't. Most, again, are named after the location. Let me just get to where I want to go here. Everything's slowed down today. Okay, when we're looking at the veins, first off, we have the main veins, the vena cava. Superior is above and inferior collects the blood from below. Now, I want you to realize that when we're talking about veins, veins collect the blood and take it back to the heart. So we're actually going to learn them in the opposite direction, the blood flows, just to keep it easier for you. And keep it easier for me, because that's the way I learn it. And again, it's very confusing, but if you think of the location, it will help you. So, brachial cephalic vein. So when we come, here's our superior vena cava, and again, we're going opposite the way the blood flows. So brachial cephalic. And then it goes underneath the clavicle. So it's the subclavian. it goes to the armpit, axillary vein. Then there's the one on the inside, the basalic, right here, okay? And the one on the outside is the cephalic. Cephalic, basalic. And then the medial cubital vein, and that is the one where you most commonly draw blood from. Okay, so let's go again. Brachiocephalic, subclavian, axillary, and then down. Now notice on the left side, you go right to the subclavian. You don't have the brachiocephalic. So you go to brachial or subclavian, cephalic, basalic, cubital, and radial. And again, think of where the location is and it'll make more sense. If you go up to the head, remember the arteries were called carotid, the veins go jugular, and you may have heard of your jugular vein. Your jugular vein is the one that goes up, collects the blood from your head. Okay, good. Cephalic, subclavian, axillary. Outside is cephalic, inside is basalic. Medial cubital, remember your, I don't know if we talked about, the cubit is a fancy word for elbow. No, your cubit is, yeah. Good, and then we go to the radial. Lovely. Let's look at the gut. When you look at the abdominal vessels, you need to know what your organ is. So, first one is the one that collects blood from the liver. Hepatic is your liver word. Then you have, that's all then all the rest of the ones collecting from the gut, these veins will be talked about when we talk about the portal system, because the hepatic portal system collects the blood vessels together and takes it all to the liver. So we'll talk about that later. Then the inferior vena cava splits about the ilium. Remember, the ilium is the top bone of your hip. It splits into the common iliac, and then outside is external, inside is internal. Once it gets to the femur, it's the femoral. Then you have the popliteal, which goes behind the knee, the fibule, which goes over the fibula, and then the main one is the anterior tibial and posterior tibial. One vessel that doesn't make any sense because it is a different name. Well, saph means vessel. So the great saphenous vein. So the great saphenous vein is the one that comes off here and goes superficial down the leg. And this is the one that usually is the one causing the problems with varicose veins. And it is also the longest vein, and it's easily to be harvested if you need a blood vessel somewhere else, because it's just collecting it's just collecting your blood at a surface level, and your femoral blood will continue to collect the blood if you need it at another one. So the great saphenous vein is the one that's used for coronary bypasses. And again, the saphenous vein is the only one that doesn't make any sense in terms of the location. All the rest are kind of based on location. Okay. The portal system. This one is important because it's confusing. But the portal system, and it's called portal because it ports the veins. Where's my title here? Very important. There we go. Hepatic portal system. So the hepatic portal system is the system that collects all the blood off the guts. And if you can think of the fact that it's just collected off all the organs and all that digestive stuff needs to be processed. So all these blood vessels go, and they go in a common one called the hepatic portal vein, and that sends it to the liver. And then the hepatic vein collects it off the liver and puts it into the superior or inferior vena cava. Okay? So the mesenteric veins collect from the gut. The splenic vein collects from the spleen. The gastric vein collects from the stomach. Okay? Blood from the capillaries of the spleen, stomach, pancreas, gallbladder, and intestines flow into the superior mesenteric and splenic vein, which converge at the portal vein. Then the portal vein passes through the liver. Now, anytime you're talking about drugs, drugs often talk about the first pass, and this means it has to pass through the liver. So anything you take orally has to be, it has to survive the digestion of the stomach. Then it also has to survive this filtering of the liver. So when the blood is collected off the digestive organs, it goes through these sinusoids. I lost my pen again. It goes through these sinusoids and then into the hepatic vein. So there's the hepatic portal vein and the hepatic vein. Make sure you know the difference, because that's a great multiple choice question. And then after it's collected from, so it's collected from the guts, goes to the hepatic portal vein, into the liver, then the hepatic vein, and then to the inferior vena cava. Now this table looks a little confusing, and it is until you look at it. This has to do with the fact that there is a pressure gradient. The whole purpose of the circulatory system is to deliver nutrients and oxygen and to remove waste, but it has to do with the pressure because of the heart. Blood flows in the same reason as anything else. There is a pressure that pushes it, and this is called a pressure gradient. So when you look at the, let's put on my marker again. When you look at the arterial end, coming off the aorta, there is a very high pressure, and that's because as the ventricles contract, it will go up to about 110, 120, and when the ventricles relax, you're down to 70. And that pressure, as the blood moves away from the heart, the pressure drops. Then it will hit the capillaries. Capillaries are smaller, but there is so many of them. It's like a river flowing into a great big lake. That will cause the pressure to drop. Then when you're in the venules and all the way to the vena cava, you have very, very low pressure. So you need another way to get the blood flowing. And we'll talk about that in a minute. Now, the highest pressure is systolic and the lowest is diastolic. So when we're talking about blood pressure, it's systolic over diastolic, or the way I remember that is sky over dirt. Systolic pressure normally is 120 over 80 is normal blood pressure, but it's a range based on health, age, and also activity level. Now, it's very important that your blood pressure, you maintain it within a proper level, because too much pressure is not good for the vessels of the system. Just like if you have a hose and you put pressure on that hose, it could cause the pressure of the hose. The pressure could cause the hose to burst. 3 things that affect it. Cardiac output. Remember how we talked about cardiac output had to do with blood pressure and, sorry, excuse me, has to do with stroke volume and heartbeat. So if your cardiac output is increasing, your blood pressure will increase. When the cardiac, which makes sense. If your heart's pumping more and you're getting more out of your heart, your pressure will increase. Now, volume. If you put more stuff in, you will have higher pressure. So if you turn the hose on more, so you have more water coming out, your pressure is higher. So and then resistance is the opposition to flow. So if you squeeze the hose when you're watering your plants, the pressure will be greater because you're slowing down the flow, but the pressure is greater and it sprays farther. Okay, so think about it in terms of, I like to think about it in terms of just turning on a tap, because then it's something you can see. Increasing cardiac output, you will increase your blood pressure. Increasing your volume, you'll increase your blood pressure. And increasing your resistance, you increase your blood pressure. And quite often, it's called the silent killer because a lot of people don't realize they have high blood pressure, even though it can be easily detected. I'm not too sure how accurate the blood pressure guides are at the Walmart and drugstores. I haven't used them lately. There is a range for blood pressure, and the range for normal is 120/80, but it usually goes to 140 to 120 is now a normal range. Textbook normal is 120/80, and I think it's 80 to 90. I'm not sure what the low is. All I know is that I'm high normal, which isn't good. I need to take care of my blood pressure so I don't have a heart attack. Okay, so that's normal. Now, again, we talked about resistance, and if you think about resistance in terms of what you're doing to hose when you water the garden, it will make more sense. If you were, peripheral resistance is to prevent friction from blood against the walls. And if you're things that'll slow down your blood could be blood viscosity. Remember how we talked about thickness? And this is why people with high blood pressure will take blood thinners, which basically just absorbs more water. Then you have the diameter. Again, if you squish a hose, the pressure will increase, but the flow will decrease. And then if you let go of your hose, your pressure will increase and your flow will decrease. So these are all factors that affect your blood pressure. Vasodilation and vasoconstriction, two cool words, but you know what? They pretty much make sense in life. Good. Now, since we talked about viscosity or velocity, which is your speed relating to your blood pressure, this makes more sense. Your aorta has although it's very wide, there's only one of them, so the blood comes out quite fast. As you increase the number of capillaries, although they're smaller, you have more of them, so that will slow down the speed of your blood, which is kind of handy because now you've got things going a little slower for a better exchange. Then as you increase the vessel size again, it will increase the pressure a little. However, there's not enough pressure to actually move it, so you need another way to get your blood to move through your... While we're talking about movement, let's jump ahead a bit. Your veins, if you remember, do not have the muscles to help you move. The veins themselves are very thin muscles, so they can't squeeze the blood itself. However, the skeletal muscles will help pump it. And that's one of the advantages too of the veins, is that the skeletal muscles are usually beside the veins. And then the veins can, the muscles will push on the veins and the blood will go to a certain amount and then the valve will stop it from going backwards. And this is a very, very good example here is if your feet are getting tingly because you're sitting too long, all you got to do is pump your calf muscles by moving your feet, flexing and extending your feet, and that will help move the blood back up and stop it from pooling in your feet. So that is the skeletal muscle pump. The respiratory muscle pump has to do with the fact that as you breathe, which we'll talk more about in Unit 17, I think it is. As you breathe, sorry, 18. As you breathe, your chest capacity, your chest volume increases, and that creates a low pressure, which also helps draw your blood up to your heart again. So the respiratory pump is the moving of the chest cavity. The skeletal pump is the moving of the skeletal muscles, usually in your arms and legs. When we look at the regulation of blood pressure and blood flow, it's auto-regulated. Isn't that amazing? There are receptors in your kidneys and in your heart and in your lungs that will regulate your breathing rate. If you have low oxygen, which will produce, so if you are not breathing very heavily, you will have a buildup of carbon dioxide, and that buildup of carbon dioxide will actually cause a decrease in pH and make your blood a little more acidic. And then that will be detected, and that will say then increase your blood vessels or increase your breathing rate. You also have a receptor, baroreceptors. Anything with baro has to do like barometric pressure. That has to do with pressure. Baroreceptors are in your carotid sinuses and your aortic arch. So that means in your carotid artery, which is the artery going to your brain, and in the top of your aorta, areas that should basically have the highest pressure. Plus, you want to make sure you don't have too high a pressure going to your brain because it'll damage those delicate brain cells. They will detect any changes of blood pressure and will transmit it through your brain and then through your glossopharyngeal and vagus nerves, which will slow it down. You have a vasomotor center in the medulla oblongata. So your medulla oblongata will then detect this pressure change, and usually if you're low, you vasodilate or you vasoconstrict, making it higher, and your heart pumps faster, making it higher. If your blood pressure is too high, you will vasodilate and your heart and stroke volume decreases. And that is okay, hormonal. Let's look at hormones. We'll look a little bit more in the hormonal regulation of the blood pressure when we talk about the kidneys, because the blood pressure is usually regulated by regulating your blood volume. So renin, angiotensin 1 and angiotensinogen 2 are regulated by, the detector is in what's called the juxtaglomerular apparatus in the kidney. Then you have aldosterone, which is regulated again by the adrenal cortex. That is, aldosterone is regulated. That's part of the renin, angiotensinogen, aldosterone. And then aldosterone will absorb more water. Antidiuretic is regulated by your brain in your posterior pituitary, and that will control absorbing more water. Epinephrine and norepinephrine are sympathetic nervous system hormones, and they're basically, when your body is stressed, if your blood pressure is too high, you vasoconstrict. You vasoconstrict. Yes. If your body is stressed, your epinephrine and norepinephrine will cause vasoconstriction, and that will cause an increase in your heart rate because those are sympathetic hormones. Okay, and then there's another hormone that will cause your blood pressure to fall, and that is the atrial natriuretic peptide. Atrial means it's in the atrium of your heart. So if your heart is feeling too much pressure because your blood pressure is too high, it will release ANP, and the ANP will cause your heart rate to cause vasodilation and your heart rate to slow down. Just know the regulation briefly. We'll talk more about those hormones when we talk about the kidney at the end. Okay. A lot of terminology there. One word we needed to talk about was anastomosis and the spelling of it. So there it is. Anastomosis. So Ana means together, or Ana means apart. Anaphase means separate. I'm gonna look that one up. Ana, I think, means separate. Stomosis means kind of like yeah, forget it. Anastomosis. So let's try that again. Anastomosis is how you say it. Anastomosis. Okay, that's enough. This one went on too long, and it is painful because all the naming of the blood vessels. So take your time, look at them, and name them. And that is the end of the vascular system.